Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. Ant. In this new lecture tutorial series, I'll go through these chemical reactions. This is for the Cambridge International O-Level examinations, the contents of which are suitable for any 14 to 16 years old IGCSE, GCSE curriculum all around the world. This is about reversible reactions and equilibrium. So candidates are expected to be able to, identify a couple of things. The first of which is this reversible arrow. If it is not big enough, I'm going to show it in a bigger manner. This is going from left to right. It's a half-headed arrow. This is going from right to left, another half-headed arrow. This symbol represents reversible. Reversible reactions mean you can go from reactants on the left to products on the right. And you can also go back from products on the right back to the left hand side, that is from the product to the reactant side. So essentially that is what we call the backward reaction. So if I use this analogy, this is going from left to right, that is called the forward reaction, the forward step, and then this is going backward from right to left, this is called the backward. So some teachers and some books, they will call this the reverse reaction or the backward reaction. So in terms of hydrated versus anhydrous substance, this is about water of crystallization. So we know about these reversible arrows. So before I talk about water crystallization, let's just talk a little bit about this reversible arrow. This reversible arrow represents reversible reactions that can proceed in both directions. So as I did mention, this only applies when your reactant is not 100% converted to products. So it's not 100% conversion because not all the reactants go to products. That is because some of the product actually go back to the reactants. Now this is an energy profile diagrams. So typically when we draw energy profile diagram, we will have reactants energy level. And then this is an exothermic reactions because from the reactants to the products, so from the reactant energy level to the product's energy level, that is your enthalpy change, that is going to be negative because it is coming down. So this is what you call an exothermic reaction. An exothermic reaction. On the x-axis, you have progress of reaction. That means how much the reaction progress in going from the left to the right. That is your reactants going to the products. The forward reaction, as I did mention, is from the reactant to the products. So to go from reactant to product, you need to overcome this mountain. This is the minimum amount of energy, that the reacting particle must have before they can react. So you must overcome this much activation energy. This is for the forward reaction. But remember that for the reverse reaction, also known as the backward reaction, that is going from right to left, in going from product to reactants, I need to overcome this much of a barrier. So it's going from this starting material all the way to the top of the peak, that is called activation energy. This is for the backward or the reverse reactions. Both these arrows are heading upward. That is because activation energy is going to be positive. It's going to be an energy that you need to overcome. Equilibrium can only occur in a closed system. So you got to know the definitions of reversible reactions, you got to know the definitions of equilibrium, and you got to know the definition of closed system. What is meant by closed system? None of the substances are added or removed. No reactants are added, no products can leave the system. Everything stays within the closed system, nothing comes in, nothing goes out. That's the whole idea. Etc. What else do we talk about? We talk about water crystallization as part of the syllabus earlier. So we know that hydrated substance, that means it is chemically combined with water molecules, and this is the key thing, crystallized within its lattice. So hydrated substance is not a liquid. In fact, it has water of crystallization. The water of crystallization is not present as a liquid. It is present as part of the lattice, which exists as a solid. So this exists as a solid. When we talk about hydrated substance, that exists as a crystalline solid typically. That's why that's crystallized within the lattice. This is a fixed definition as stated in the syllabus. Whenever we talk about hydrated substance, we are not talking about something that has water. It is something that has water of crystallization, and these water molecules are trapped or crystallized within the lattice. That's why it exists as a solid. It is never a liquid. On the other hand, you have this thing called anhydrous. Anhydrous means you have already removed all the water of crystallization. So you already taken away all the water of crystallization. So if you have no water crystallization, there is just no water molecules present in your formula units. And when you have water crystallization, these two are the common examples as stated in the syllabus. This is what you call hydrated copper 2 sulfate, because this is copper 2 plus, and then sulfate salt come from sulfuric acid. So sulfuric acid H2SO4 replace the 2 of the H plus with a Cu2 plus cation. You get this copper 2 sulfate, hydrated copper 2 sulfate. Copper 2 follow the oxidation number of the copper there. This is called cobalt 2 chloride. So you've got CO2 plus, Cl minus. You got 2 of these because the charges need to cancel out if you think about crisscrossing and the formulation of the ionic compound formula. This is plus 2, this is minus 1. That is what you call cobalt bracket 2. Just like earlier, you have copper 2 sulfate. Here you have cobalt 2 chloride. This is hydrated because you have the dot. You pronounce this as dot. COCl2 dot 6H2O. We pronounce this as CuSO4 dot 5H2O. You're going to have observations when you heat this to dryness, meaning to say heat until constant mass, meaning to say you remove all the water crystallization until no more water crystallization come off. The first observation that is common for both of them is that you get a colorless liquid. You cannot say it's water because you did not test for it, you did not test it personally, and you just see colorless liquid. Observation, what do you see? You cannot see water because you don't even know if it's water, but you know it's colorless, you know it's liquid, you know it condenses on the upper part of the tube. This is going to be the cooler part of the tube. So when you have the solid there, as I apply the heat there, you are going to get a little bit of water forming. So these are the colorless droplets. You can say colorless liquid droplets form on the upper part of the tube. This side is hot, this side is cold. As it vaporizes, the water crystallization vaporizes under the intense blue heat of a Bunsen burner, and then the water vapor escapes as a gas. But then when you reach the colder part of the tube, it's going to condense. Condensation is basically gas going back to liquid, and then that will turn back into these colorless liquid droplets at the upper part of the tube. Very common practical question. Alternative to practical question could also be a theory level question. This is the test for water or water vapor, the test for H2O as a liquid, the test for H2O as a water vapor. You can either use anhydrous copper 2 sulfate without the water crystallization. This is a white solid, it turns blue solution. And then this anhydrous cobalt 2 chloride started as a blue solid and then it turns to a pink solution. This is wrong. The way to write it will be CO2 plus as a charge and then aqueous ion there. So just a brief recap, copper 2 sulfate is going to be blue when it's hydrated, and then the copper 2 ions are surrounded by water molecules. This is called water crystallization. There are water molecules trapped within the crystalline lattice, and this reaction is reversible. So in the reversible reactions, you got to balance your equations. This is a solid going to solid. As you apply heat, the water crystallization comes off. They come off as a liquid, but actually they vaporize first, but then they're going to condense in the upper part of the tube as liquid water. So this is 5H2O molecule, CuSO4 dot 5H2O. When you calculate the MR is going to be the MR of CuSO4 plus 5 times the MR of H2O, because you have dot 5H2O, you have 5 water molecules like that. And of course, balance the equation with 1 CuSO4 and 5H2O being kicked out. Cobalt 2 chloride similarly is reversible reaction, so you can go from left to right, right to left. Balance the equations. Cobalt 2 chloride hydrated has got 6 water of crystallization. Copper 2 sulfate has got 5 water crystallizations. We got to think about the colors. So this is a hydrated copper 2 sulfate that is blue in color. There's a blue solid, and this is a white solid. So anhydrous copper 2 sulfate is white in color. On the other hand, you have cobalt 2 chloride hydrated. This is going to be pink. Oops, I think there's pink. Yeah, there's pink. And then this is the pink solid. And when you remove all the water crystallization, it's going to be a blue solid there. And that's essentially summarized in this table here pretty nicely there.
Metals, they form, very special about them, they form colored compounds. If you get colored complexes that contains metal cations, colored complexes that contains or colored compounds that contain metal cations, most likely it contains transition metal. Transition metal is that P is that region in the periodic table. You know, that's middle region. Those are the transition metal series. And copper is Cu, is just there. This is copper to sulfate, blue color crystals. You might have done crystallization of these. This is copper to sulfate, pentahydrate. If you look carefully, copper to sulfate, they don't say it's hydrated, but if you look at the formula, CuSO4.5H2O. I think I'm just going to do the example here to show you again how to calculate the relative molecular mass. So we have copper 2 plus, because it's copper 2 sulfate. So 1 copper, so 1 times 64 plus 1 times 32 for the sulfur, plus 4 times 16 for the oxygen. And then the dot simply means in the giant ionic lattice of copper to sulfate, which is an ionic compound, cations, anion, copper 2 plus, SO4 2 minus. I have 5 water crystallization, so 5 times 2 times 1 plus 16 times 1, or you know the molecular mass of water because of 2 hydrogen and 1 oxygen atom is 18 or 18.0. So altogether I have these Mr for the copper to sulfate plus the Mr for the water times by how many water crystallization. 64 times 1 plus 32 times 1 plus 16 times 4, I get 160. And then I have 5 water crystallization, so 5 times 18, that's 90. And I get 250 to the nearest whole number. If you look at these are the more accurate molecular mass. Not sure how clear it is. 5H2O, the molecular weight is close to 250. I think it's 249 point something, because they are using a more accurate relative atomic masses. Okay, cobalt chloride with the water H2O. It was this color. So this is already a very old sample, the test paper. That's why you have this thing turning pink, because the water vapor in the air already turned all the supposedly blue, should have been blue. Okay. What I'll do instead is I will show you by heating this letter. I remove all the water of crystallization and then it will become blue. Because once I remove all the water, I only have the thing there that will become blue, and that is actually what is used to test for water vapor. That is, it will become blue, and they actually use it to coat the filter paper. And when you have water in contact with the cobalt to chloride blue colored thing, and then it will turn pink again because it will form the hydrated compound. On a copper 2 sulfate, hydrated, this is copper 2 sulfate with 5H2O. So this is a blue color solid, as I've shown you, very, very crystalline, like that. I will just take a little bit out, Go away. Really should have goggles and safety glasses and my lab coat. This is a blue color solid, as you can see, very crystalline. You can hear the sound. It doesn't stick on the walls of the thing because it's dry. When your test tube is dry, you should not have any solids stuck on the side at all. The upper part is dry, the lower part is dry. Okay. This was copper 2 sulfate with 5 water of crystallization, which of course you know how to calculate the molecular mass already. That was one of the earlier exercise. Okay. In qualitative analysis, they like to ask you to work out the identity of the cations and stuff. In A levels, they like to ask you the case study of copper 2 plus and cobalt 2 plus among many other transition metals. But here I'm just showing you the water crystallization will come off first when you do thermal decomposition. If it does decompose, the water crystallization always come off first, right? So because water boils at 100 degrees Celsius. Bunsen burner, 100 degrees Celsius, very easy to reach when you have the blue color flame. So let's start heating. just bring attention to this. You could see that the blue color solid has slowly turned white. So there's a bit of white solid now. And then there is a condensation, and this condensation is not colored, it's not blue in color. As you could see, it is a colorless liquid. These are liquid, these are not gas because they condenses on the upper part of the tube. I touch it outside and doesn't do anything because the liquid is actually inside. Because your water vapor was inside, your steam was inside, it condenses on the upper part of the tube because the compound has water of crystallization. This is what you see. You see a colorless liquid form on the upper part of the tube. This is also what you see. The blue solid has turned white. I will hit it more strongly to get rid of all the water of crystallization, and hopefully it should make more sense in a little bit. The fire is not that strong, so I'm hitting it a bit strongly now. And as I hit it more strongly, then all the water of crystallization will be driven off. Here it's very easy because you can see the color change. Whereas for the white colored solid, it's very difficult to tell, right? If you have gotten rid of all the water or not. Okay. So here you can tell that they already turned whitish, and they're already kind of stuck on the side. So I do not want to hit it even more strongly because I'm hitting using a test tube, and I do not want to break my test tubes. Okay. So that was the copper 2 sulfate hydrated. The blue solid has gone. The blue solid. Oh no, where am I? Right. There was a copper 2. This was the copper 2. They give you the white color solid. Alright, so copper 2 sulfate hydrated. This was the hydrated salt that I heated just now. Remember, we started with very blue colored solid, very blue colored crystals. That was hydrated. In the absence of the water crystallization, the upper part of the tube is just water. In the absence of water, because I heated very strongly, you don't see any blue colored solid at all. They are all white colored solid. And because there's anhydrous, and I do actually have copper 2 sulfate anhydrous. Anhydrous means no water of crystallization. And let me look at the molecular mass. You see they only label it as CuSO4 because that is without the water crystallization. It's a bit bluish, probably because this has been around for a long time, so it's absorbed a little bit of water from the atmosphere. But if it was freshly heated like this to remove the water crystallization, it would have been white. Okay, and I'm just going to add water to this anhydrous copper 2 sulfate. What do you notice? Alright, what do you notice? So they can ask you this in a qualitative analysis experiment, not just in O-level, but most likely in A-level, I guess, where they give you a blue color solid, they ask you to heat it, and then you see colorless liquid form on the upper part of the tube, the blue solid goes white. Okay, you heat strongly until it goes white, that's the observations, and then you add water to it after it cools down, and you get a blue solution again. The fact that you get a blue solution again, okay, refers to this idea of reversible reactions. In the presence of water, the anhydrous copper 2 sulfate gets surrounded by water molecules again, and they reform that hydrated compound, okay, which you can then purify by crystallization, or better hold it tightly. Purify by crystallization, and you can get the hydrated crystals where the water as the solvent can co-crystallize, meaning they crystallize together with the giant ionic structure of copper 2 sulfate.
Whereas in the presence of water, the blue solid will turn pink. The white solid will turn blue because there is copper 2 sulfate anhydrous become copper 2 sulfate hydrated, which then dissolve in water to give you the Cu2 plus aqueous. The cobalt chloride, the cobalt 2 chloride anhydrous become the pink solution from blue to pink. Make sure you write the charge of the ion correctly. I have done that mistake there. Okay, so just in terms of the observations, these reactions are reversible. Reversible means they can go both way. So you have learned that in the sense of partial dissociation of weak acid into H+. This is not partial dissociation into weak acid. This is just reversible. It can go from left to right. You can go from right back to left. These are the important color changes. Make sure that you know about these color changes as the syllabus does require you to do that. The hydrated copper to sulfate is blue. It goes to white when you remove all the water crystallization. This with 6 water of crystallization is pink. Hydrated cobalt to chloride is pink, and then it becomes blue. So typically we would use the blue anhydrous cobalt to chloride to test for water vapor. In the presence of water vapor, this becomes hydrated, and then it will form the pink solid from blue to pink. If you have copper to sulfate solid, in the presence of water, they will become hydrated. It will go from white to blue there. Okay, so hopefully that makes sense. In between this, I'll append in some experimental tutorial video showing you these particular color changes. And apart from that, yeah, I mean, that's it really. Compared to the test tube, so this is a pink solid. We will heat it. If I heat the pink solid, it's a hydrated salt. So first thing that comes off will be the water of crystallization. How you can see now it is blue, just now was pink. There's a bit of condensation on the upper part of the tube, and if I heat it further, it will become more obvious. It's the water crystallization that is coming off. So the water crystallization is coming off, you get a colorless liquid formed on the upper part of the tube. Hot end, cold end, water crystallization escape as steam, and when they reach the cold end, they will condense. You get a colorless liquid. This was a colored compound, so it all makes sense hopefully. So hydrated cobalt to chloride was pink in color, and this is what you call, this blue color is what you call anhydrous. Anhydrous because you remove the water crystallization and it's blue. So what happened with this blue color solution is, if I add water to it, it will become hydrated again, and we use anhydrous cobalt to chloride paper, which is filter paper coated with this anhydrous cobalt to chloride to test for water vapor or water, and it will turn pink. I'll wait for a bit until it cools down before I add water to this hot glass test tube. It's very dangerous to add water to a hot glass test tube, okay? So I think my test tube has already cooled down. Remember, I had the hydrated cobalt to chloride, which was pink, and also pink in solution. Now this was the heated one. Some of it has turned a bit pinkish because of the water vapor in the atmosphere. So this is cool now. I can add distilled water to the blue color solid, which was supposed to be anhydrous, because I drive off the water crystallization. And you notice that the solution again is pink, because in the presence of water, it gets hydrated again. Next bit of the syllabus basically says candidates should be able to, I think there is a typo there where I've typed it multiple times, state that a reversible reaction in a closed system. We said that a closed system, just a reminder, nothing comes in, nothing leaves the system. Nothing comes in or leave the system. The system is in equilibrium, so nothing comes in, nothing leaves the system. That is called closed system. You are at equilibrium when you have these two conditions satisfied. A lot of students always get confused between the two conditions. The first of which is what you call the rate. The rate of forward reaction is equal to rate of reverse reactions. If you don't like to use the word reverse, you can use the term backward. It's entirely the same. And then the second bit of the definition is that the concentration of reactant products are no longer changing. This is the key thing, no longer changing. No longer changing means they remain constant. Now some students would say, oh, the rates are the same, the rate of forward and backward reaction are the same, so the concentration of reactant product must be the same. If they are the same, there is a coincidence, but it's not a requirement. These two is a requirement. It's compulsory to meet these two requirements if you want to have a system in equilibrium. You can have a reversible reaction. Things that go from solid to liquid. Liquid can go back to solid. This is melting. This is freezing. So those are reversible reaction, by the way. Okay, those are reversible. So this is melting, going from solid to liquid. Liquid going back to solid. That is called freezing. These are reversible. Reversible, yes, but then they are not in equilibrium because when you are in equilibrium, you must have a closed system where nothing comes in or leave the system. But the two conditions, your rate of forward reaction must be equal to the rate of backward reactions. And then your reactants and products concentrations must no longer be changing. They must remain constant. They must remain unchanged. So you can use either of these words. They all mean the same thing there. This is just the diagrams representing what happened to the rate. So you have the forward reactions. If I just magnify a little bit here, forward reactions. So the rate is slowing down like that, but the backward reaction is happening at the same time, and then they reach equilibrium here. This is when the rate of forward reactions and the rate of backward reactions becomes equal. So this is equal rates of forward and also backward reactions. At that very moment in time, and you can see that the concentration of products that were increasing up until you reach equilibrium. So here we can say you reach equilibrium. When you reach equilibrium, let me spell that properly because a lot of students can't spell equilibrium properly. That means the concentration of products and the concentration of reactants are no longer changing. This square brackets is just a shorthand notation of representing concentrations, but in O level, in IGCSE level, we still write out the term exactly. So the concentration of reactants and the products remain unchanged, they remain constant, they remain unchanged, so they all mean the exact same thing. So just to recap, so what do we mean by dynamic equilibrium? Dynamic equilibrium, basically when you reach equilibrium, you must already have a closed system, a reversible reaction in a closed system, by the way. And then you gotta include both condition, where that is to do with the rate of forward reactions equal to the rate of backward reactions when they meet here. And the concentration of product and reactants are no longer changing. So there is no change in the concentration of reactants and the products. Again, this is the summary of it. It's pretty much the same as the definition of dynamic equilibrium. You should be able to define that very well. Okay, so I think that's it really for this tutorial video. So I'll stop here and we'll continue more in the next part on Le Chatelier principle and explaining how changes to the equilibrium from the outside, from the surroundings, would affect how the equilibrium will respond to those changes. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Follow me at ptet.chemistry. That's at ptet.chemistry on Instagram, Facebook, Twitter, and Telegram to get connected.